So welcome back students. In the previous video we have seen numerical integration, that is problems based on trapezoidal rule, Simpson's one-third rule and Simpson's 3/8 rule. So in this video we are going to see numerical solutions of ordinary differential equation. So here we are having the five methods, that is number 1 is Taylor series, number 2 is Picard's method, number 3 is Euler's method, number 4 is modified Euler's method and number 5 is RK method. So these are the five models, very important models that we are going to see in this video. So before going to see that, we are going to see one definition, that is a general equation of first degree and first order dy by dx equal to f of xy with the initial condition y of x naught equal to y naught. This is called as initial value problem. So he will ask in the examination what is the initial value problem. Then what we have to write is a general equation. So that general equation must and should be it is a first degree and it is a first order, that is dy by dx equal to f of xy with the initial condition y of x naught equal to y naught. Then this is called as initial value problem. So this is the definition he will ask in examination. So now we are going to see each and every model. So first of all we are going to see the easiest model, that is Eulers method. So Euler's method is also called as RK method of first order. So if we learn this Euler's method, then we can learn the RK method of first order also. So that is two benefits. We are having two benefits here by learning this method. So here also he will give a differential equation dy by dx equal to f of xy with initial condition y of x naught equal to y naught. Then the formula for Euler's method is y1 equal to or y of x1 equal to y naught plus hf of x naught y naught. So the next iteration is y2 equal to y of x2 equal to y1 plus hf of x1 y1. So the third iteration is y3 equal to y of x3 equal to y2 plus h into f of x2 y2. So on we process. We repeat the remaining process until the two values are approximately same. Like this we have to do the problem. So this is the formula for the Euler's method. So now we are going to see the problems. So in the first problem he has given that dy by dx equal to xy. So he has given a differential equation and he has given an initial condition, that is y of 0 equal to 1. That means y of x naught equal to y naught. That means x naught equal to 0 and y naught equal to 1. Then we have to find y of 0.1 value, y of 0.2 value, y of 0.3 and y of 0.4 value by using the Euler's method. So first of all what we have to do is we have to write what he has given. So he has given dy by dx equal to f of xy and initial condition y of 0 equal to 1. That means y of x naught equal to y naught, and that means x naught equal to 0 and y naught equal to 1. So we have to write the formula y1 equal to y of x1 equal to h into y naught plus h into f of x naught y naught. So on substituting these values we get the y1. So y1 equal to 1. So this is y of x1 equal to y1 value. So that is y of x1 equal to y1, where x1 equal to 0.1 and y1 is 1. So next we go for y2. So that is y of x2 that equal to y1 plus h of x1 y2. So here we can observe that the next value depends upon the previous value. So that is the important point. So if the previous value is correct, then only we get the next value correct. So we have to see the calculations perfectly. So y of x2 equal to y1 plus h into f of x1 y. On substituting these values, we get y of 0.2 value, that is y of x2 value that equal to 1.01. So this is y of x2 equal to y2. So next we have to find y3. y3 equal to y of x3 equal to y2 plus h of x2 y2. So on substituting the values, we get y of x3 value that equal to 1.0302. So this is how we can find all the values, remaining all the values using the initial condition. So based on the initial condition, that means y of x naught equal to y naught, we can find y of 0.1 value, we can find y of 0.2 value, y of 0.3 value and y of 0.4 value. So here the next value depends upon the previous value. So the next value is very important. Why? Because the next values depends upon the previous value. So like this we have to substitute all the values, then we get the required solution. And the difference between that is h. Here the difference between 0 and 0.1, that is 0.1, that is h. Difference between 0.1 and 0.2, that is 0.1, that is h. 0.2 and 0.3, that is 0.1, that is h. So difference is 0.1, that is h. So that we have to remember. So next we are going to see the second problem. So solve the Euler's formula. Here he has given dy by dx equal to x plus 5. And he has given y of 0 equal to 1, that is y of x naught equal to y naught, by taking h equal to 0.1. So we already know the formula y1 equal to y of x1 equal to y naught plus hf of x naught y naught. On substituting these values, we get y of x1 equal to y1, that is y of 0.1 equal to 1.1. So that means we are having y of x1 equal to y1. So based on y of x1 equal to y1, we find y of x2 equal to y2. So we already know the formula. On substituting these values, we get y of x2 equal to y2. So based on y of x2 equal to y2, we find out y of x3 equal to y3. So by using the formula, on substituting these values, we get y3. So this is how we are going to do the problems on Euler's formula. So here he has given the other problem. So here he has given dy by dx equal to minus y. Initial condition is y of 0 equal to 1. That means x naught equal to 0 and y naught equal to 1. Also he has said to find y of 0.04 by taking h equal to 0.01. That is difference between the values is 0.01. So first of all we have to find y of 0.01 value. That means y of x1 equal to y1. So based on that we have to find y of x2 equal to y2. Based on that we have to find y of x3 equal to y3. So like that we have to find all the values, and here the difference between each and every value is 0.01. So this is how we are going to do the problem. So like this we can do the plenty of problems on Euler's formula. So Euler's formula is the simplest formula. So it is also called as RK method of first order. So next we are going to see the modified Euler's method. So this modified Euler's method is the updates of it is the update version of Euler's formula. So here we can use the Euler's formula in this Euler's modified formula. So here the formula is y1 of 1 equal to y naught plus h by 2 into f of x naught by 1 plus f of x1 by 1 of 0. See here y1 of 0 means that is y1 that equal to y naught plus hf of x naught by naught. That means it is a Euler's formula. So if you want to find the second approximation, then y1 of 2 equal to y naught plus h by 2 into f of x naught y naught plus f of x1 y1 of 1. That means up value. So here also the next value depends upon the previous value. So next is third approximation, y1 of 3 equal to y naught plus h by 2 f of x naught y naught plus f of x1 y1 of 2. Here you can observe that the only value will changes is y1 of 0, y1 of 1, y1 of 2. So these are the values that will change. So here we can find the approximations, that is y1 of 1, y1 of 2, y1 of 3, y1 of 4, like that until two values are approximately same. If suppose y1 of 3 and y1 of 4 are equal, we stop the process and we go for the other iteration. So like this we have to see that whether the two approximate values are equal or not. If the two approximate values are equal, then we stop the process and go for the other value. So next, if you want to find y2 that equal to y of x2, then the formula is y2 of 1 equal to y1 plus h by 2 into f of x1 y1 plus f of x2 into y2 of 0. That means y1 means the previous value. Already we have done this value. That means we got y of x1 equal to y1. So that value we have to use here. So the second approximation y2 of 2, the third approximation y2 of 3, the fourth approximation y2 of 4. Like this we proceed the process until the two values are approximately same. So this is the formula for Euler's modified method or modified Euler's method. So now we are going to see the problem. So here he has asked a problem, solve the differential equation dy by dx equal to x square plus y, and he has given initial condition y of 0 equal to 1, and he has asked y of 0.02 and y of 0.04 values. So first case we have to take the initial condition y of 0 equal to 1. That means y of x naught equal to y naught. So case 1, when x1 equal to 0.02, we already know that the modified Euler's formula is y1 of 1 equal to y naught plus h by 2 into f of x naught y naught plus f of x1 y1 of 0. So first we have to find y1 of 0. y1 of 0 or y1 equal to y naught plus hf of x naught y naught. So we have to first find that value. And next we have to find y1 of 1, that equal to y naught, that is 1 plus h by 2. H already has given 0.02 by 2 plus y naught value already has given 1 plus f of x naught y naught. Already we know x naught y naught value. So x naught y naught values are, this is like f of xy. Already has given f of xy equal to x square plus y. That means 0.02 square plus 1.02. Then we get the value. So like this we got y1 of 1 equal to 1.0202. Next iteration, next we are going to see the second iteration. That means y1 of 2. On substituting the value, we got y1 of 2 equal to, that is y of 0.2 equal to 1.0202. So now we can see that y1 of 1 and y2 of 2, they both are approximately same. So next we should not go for the other iteration. Why? Because these two values are approximately same. So we stop the process. So we are getting the value. Therefore, the answer for this is y of 0.02 is 1.020. That means this is y of x1 equal to y1, where x1 is 0.02 and y1 is 1.0202. So next we go for the case 2, when x2 equal to 0.04. So the case 2 depends upon the case 1, the values of the case 1. So next case 2, when x2 equal to 0.04, we have to write the formula y2 of 1 equal to y1 plus h by 2 into f of x1 y1 plus f of x2 y2 of 2. So on substituting these values, we get the y1 of y1 of 2 value or y2 of 2 value. So we can see that y2 of 1 value and y2 of y2 of 1 value and y2 of 3 value, these both are same. So we stop the process. So next we will see the other problem. Solve the differential equation dy by dx equal to y minus x by y plus x. Initial condition y of 0 equal to 1. So similarly, we can see that initial condition is y of x naught equal to y naught, that is x naught equal to 0 and y naught equal to 1. So case 1, when x1 equal to 0.1, we write the formula and substitute all the values, then we get y1 of 1 equal to 1.0917. So next we go for the other iteration, that is the second iteration y1 of 2. Next we have 1.0916. So by this we can observe that y1 of 1 and y2 of 2 are slightly different. So we go for the other option. So y1 of 3. So now we can see that y1 of 2 and y1 of 3 are approximately same. So therefore the root for the given equation is 1.0916. That is y of x1 equal to y1. That is x1 equal to 0.1 and y1 is 1.0916. Next we go for case 2. That means when x equal to 0.2. So same formula. y2 of 1. Here is second approximation. So y2 of 1 equal to y1 plus h by 2 into f of x1 y1 plus f of x2 y2 of 0. So first of all we have to find y2 of 0. Then after that we have to substitute all the values which we have given and we get the approximation. So similarly I got the approximation y2 of 1 equal to 1.1687. So similarly y2 of 2 equal to 1.1686. And next these two are not approximately same. So I go for the other iteration. So y2 of 3 equal to 1.1686. So I can observe that the two values are approximately same. So I stop the remaining process. So this is how we do the problems on modified Eulers method. So here are some problems done by modified Eulers method. You can easily do this problem. So if you are having any doubt in this modified Eulers method, so you can ask me. So this is the important and very easy method. It is easy to understand. The only thing we have to remember is formula. So if we remember the formula, then we can easily do plenty of problems based on this.